Hello everyone, this is our video on Niels Bohr. Please take out your handout so you can start taking notes. Niels Bohr was born in 1885 and he died in 1962. He was born and died in the same city, Copenhagen, Denmark. He studied at the University of Copenhagen, where he majored in physics. Then in 1911, he traveled to England, where he met, guess who? Yes, J.J. Thomson. He met J.J. Thomson at the University of Cambridge. He also met Rutherford, who invited him to conduct a postdoctoral work at the University of Manchester. So Bohr was mentored both by Thomson and Rutherford, and he also collaborated with other scientists, including Werner Heisenberg and James Chadwick later on in his life. Bohr had to leave Denmark when it was occupied by the Germans during World War II, and along with Chadwick, he participated in the British mission to the Manhattan Project. After the war, he was involved with the establishment of the CERN, which is the European Organization for Nuclear Research, and he promoted international cooperation for nuclear energy. Now, let's begin talking about his work. So we know Niels Bohr because he developed the Bohr model of the atom. In this model, he proposed that energy levels of electrons are discrete and that electrons revolve in stable orbits around the nucleus of the atom. What does that mean? Well, let's begin with the word discrete. A discrete value will be a value that we can actually count. For example, the number of students in a classroom. I can count 26 students in my classroom or 18 students in my classroom. However, I cannot have 19.5 students in my classroom. 19.5 will be an example of a continuous value. And a continuous value would be a value that can measure from 0 to infinity, and it depends on the equipment. Again, we're talking about a plus or minus value for uncertainty. For example, if I tell you that I measure 1.72 meters, well, that depends on the instrument I use for measuring. For example, if I use the better instrument, I can tell you that I measure 1.725 meters. And if I use even a better instrument, I can add another decimal place to that number. So that will be an example of a continuous value. With that being said, let's continue our video to see how Bohr's model looks like. When Bohr was working with Rutherford, he realized that Rutherford's model wasn't quite right. By all rules of classical physics, this should be very unstable. For one thing, the orbiting electrons should give off energy and eventually spiral down into the nucleus, making the atom collapse. Or the electrons could be knocked out of the position if a charged particle passed by. So Bohr decided to solve this problem because the model that Rutherford had proposed didn't look stable to him. And to try to solve this, Bohr turned to quantum theory. Now, quantum theory was discovered by Max Planck, a German physicist, and Max Planck starting working with the nature of energy. So he came up with the idea that energy, instead of being continuous, comes in distinct particles, and these particles he called quanta. And quanta is from the Latin how much. So instead of having continuous values, we would have discrete values. And this is where Bohr uses this term discrete. So he will now propose a model that is using discrete values or quanta values to describe how the electrons move around the nucleus. And Bohr will be the first one to suggest the revolutionary idea that the electrons jump between energy levels. These energy levels are what we call the orbits, and in these orbits are discrete. So here we have a value. We see this has an energy level of 1, which is the first orbit. Then we have energy level of 2, it's the second orbit, and so on. Okay, so n equals 3 will mean that we have an energy level of 3. Now here we see the electron, okay? Electrons are in the orbits that have quantized sizes and energies, and when the electrons jump from one orbit or energy level to the other, they either emit or absorb energy. And this energy can be given off as light or as heat. And again, when the electrons jump from one level to the other, they will either absorb or emit energy. Now, when do each of these happen? Well, energy is emitted from the atom when the electrons jump from one orbit to another one that is closer to the nucleus. So when they're going in this direction, like the diagram we have here, energy is emitted from the atom. And this model that we have here is also called the planetary model because it resembles the, the planetary system. Okay, so our center will be the sun, and then we have planets orbiting around the sun. Let's take a look at Bohr's atomic theory. So number one, neutrons and protons occupy a dense central region. That's the nucleus, and that's the same as Rutherford and Chadwick had proposed. The number two, electrons orbit the nucleus in stationary orbits defined by their angular momentum, and this is something Bohr proposed. Number three, electrons can jump between orbits by emitting or absorbing a quantum of discrete energy, and here we have the concept of quantum mechanics applied to the atom for the first time. Another thing is that the overall change in energy associated with the orbit jumping is the difference in energy levels between the ending and the initial orbits. So let's suppose that we have an electron that jumps from a level 1 to a level 5. The final state will be a level 5, so here we would have a 5 minus 1, so we have a change in energy of 4. That's how this works. Over the years, more scientists will come that will refine Bohr's theory. However, his bold application of new ideas paved the way for the development of quantum mechanics, which is extremely important. Now I will leave a link to a video. Well, actually, I'm going to show you a video that explains in a very visual way what I just tried to explain to you. I know this is something probably with the Bohr model of the atom we can easily understand because it looks like our solar system, but later on we'll see with quantum mechanics that it starts to get very confusing. So I will show you a clip that explains how Bohr's atom should look like. Thanks for watching, and I'll see you in class.
It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained one proton and one electron. But the scientists of the time could think of no stable arrangement of the two particles. It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus. Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. And the energy of this radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen, when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbits. But no one was certain why only those orbits were allowed.